This is part B of the kind of intro to nuclear chemistry notes. We're going to focus on writing nuclear reactions. It will be helpful to have a periodic table available. I did put one at the end of your student note sheet. So if you haven't scrolled to that fourth page yet, there is a periodic table there for you. It is also linked. There's one linked on Schoology if you want to open up a separate document. So since we're dealing with nuclear chemistry, that chemistry of what's in the nucleus and how our atoms are going to change to become more neutral, those protons and neutrons are what we are focusing on. We're not often going to see a charge, but we are going to use atomic notation to help us stay organized. And so the things that we're going to see in atomic notation that are going to be helpful is that mass number, and that mass number is our protons plus our neutrons. We're also going to have that atomic number, and a reminder that the atomic number, that is our number of protons that our atom has. That defines what the element is. And we put those next to our symbol with that mass number in the top left corner, and the atomic number, or the protons, in the bottom left corner. Those are the things that are going to be changing when we are looking at nuclear chemistry, because protons and neutrons are what are in the nucleus. When we've been looking at changes of an atom, we've been dealing mostly with things that have charges. And so charge, that tells us about how our electrons compare to our protons. That's in the top right corner. And we're not going to see that really anymore, even though that's something that we have seen in the past with that. And so just as a review, how many protons does the sodium have? Well, sodium has 11 protons. If we look at a periodic table, here's our sodium, those 11 protons, that's the atomic number we see in the top left corner. And then when we're looking at our different isotopes, we're going to specify what isotope it is with that mass number. So if we look at this one, because sodium has an atomic number of 11, that tells us how many protons we have, and those are our positives. How many neutrons do we have? Well, we can figure out our neutrons by looking at the protons plus the neutrons equaling the mass. I know what my mass is, so I can do mass minus my protons. That's going to tell me my neutrons. So in this case, the mass is 23 for this specific isotope, minus 11. So this would be a sodium isotope with 12 neutrons. Often we're going to have these neutral. If we were looking, though, at electrons, electrons are negative. This has a positive 1 charge, and we have 11 protons. How many electrons would I need? This would have 10 electrons because we can't change our protons. So we need to make sure that we have one more positive proton than we have electrons if we had something with a charge with that. If you ever see a hanging plus sign or a hanging minus, it just means +1 or -1 with those. So using that symbol with the mass number in the top left and the atomic number on the bottom left, that is how we are going to stay organized as we are looking at writing nuclear notation. And so when we're looking at this, you're going to have your element, that is your atomic symbol. And then we are going to the top left of that symbol, write the mass number, and then the atomic number is in the bottom left. And again, the atomic number, that's the number of protons we have. That mass number is protons plus neutrons. And so we can find neutrons if we need it. So let's practice writing the nuclear notation for the following. So carbon-14, we do need a periodic table for this. So again, if you can get that periodic table out, there's one on the last page. So carbon-14, if I go, and I'm going to scroll here, here's my carbon. So I'm going to have that atomic symbol of C. And carbon has 6 protons because that is the atomic number that we were given. So I'm going to have carbon. We put the atomic number in the bottom left, and then the mass number goes in the top right. With this notation, this is telling us we are using specifically carbon-14, and so I would put that 14 in the top left position. Let's look at our next one, uranium-239. We are going to have now some elements that we're not used to working with. As we look here, uranium is in that bottom row right here. And so we look at that. Uranium has an atomic number of 92. Sorry for all the scrolling. And I can put that here. So looking at how would we write that, well, we put our atomic symbol here. And then I'm going to go ahead and put that 92 goes in the bottom left. This is telling me that the mass number I'm using is 239 with that. If you want, go ahead and try the next couple on your own or continue to follow along and do these with me. Next, we have xenon. I went and just grabbed a screenshot of that element. So we're going to have xenon Xe is that symbol. 54 is the atomic number from the box. That's telling us how many protons we have. And then 127, this is saying we're specifically using the xenon 127 isotope, so that goes in the top left corner. So we're not using this number at the bottom, we're using the number that it says in the name. So we could write xenon 127. I could also write it like that, and I would know it's xenon 127. Iodine, we've got iodine 131, so that iodine goes there, 131, and iodine is number 53. And if you haven't yet, try the next couple on your own, pause the video and come back. We've got polonium, PO, that's number 84. And this is polonium 208, so that goes in the top left. Protactinium is PA with that 211, and then 91 is the atomic number. So we do this because it gives us information about our protons in the nucleus and everything that's in the nucleus. The mass numbers are protons combined with our neutrons. It's less work for us to do this than to split it into just the neutrons. One thing we are going to see is if we have an electron, when we are looking at that, we actually, for an electron has no mass, but we are going to use a -1 because an electron is a negative particle. And so that means it's going to, if it's losing an electron, it's going to have a -1 for the proton. And so that is something that we will see. And you should have in your previous set of notes when we were looking at our beta decay. Beta decay is where an electron is released or lost. And so that is something that we will see, and our notation for that electron is given here, which you hopefully saw when you watched the crash course video. So how do we use this notation and how do we look at nuclear reactions? So a nuclear reaction happens as the particles in the nucleus change in an attempt to become more stable. We show the before and after atoms, making sure all of those subatomic particles are conserved throughout. And by all, we're focusing on the protons and the neutrons. And that's how we show that in that notation. And so the reaction below, this shows how uranium-235 is decaying to produce an alpha particle, which is that helium atom, and thorium-231. And so notice that the sum of all of the atomic masses, that mass number, all of those, we've got 235, well that equals 4 plus 231. Those are equaling on the reactants and product side. Same thing with the protons, or that atomic number in that bottom left. We see that that 92 from our uranium equals 2 plus 90. So we're seeing that that mass or those particles are conserved. So we've got some nuclear reactions here. Let's go ahead and complete this. And again, you're going to need a periodic table. Once we get to the part of figuring out what element is that. So as we look, we have something that is breaking up, and then we have this electron plus that 14/7. From that crash course video, we can see that this is beta decay, because again, that beta decay, that's when we have that electron is being released. That is a electron or beta particle with that. And so we can see a couple of these anytime we see those electrons. So these two are representing beta decay. As we're looking at this now, I have my beta particle and then I have nitrogen 14. So what was that at the start before it underwent that beta decay? Well, we have 0 and 14. As we look at our top numbers, 0 and 14, well, 0 plus 14, that's going to have to equal whatever is in the top left over here. So 0 plus 14, there we go. Now let's do the same thing with our protons. We've got -1 and 7. We do have to be careful. This is a -1, so -1 plus 7 because of that electron. Well, that's going to give me a 6. So what element is that? I need to go to my periodic table, and I'm going to look, well, what element has 6 protons? And that is carbon. So I can fill in my atomic symbol, what element that is, once I know how many protons I have. All right, looking at number 2, it looks like we have some particle plus a hydrogen is going to produce carbon 12, and this helium atom, as we look at this helium, anytime we have that decay with that helium particle, that is called alpha decay. So alpha decay is when a helium 4,2 helium, when that gets split off from your original with that. And this one we do also have a hydrogen particle, so maybe there's a collision before this happened. As we look at this, let's look at now, again, adding up. We've got 4 plus 12, so I have 16 on this side. On this side, I've got 1, and I'm going to need something else. So what plus 1 is going to give me that 16? Well, I need 15 plus 1, so I'm going to have a 15 in this top left here. 15 plus 1 does equal 12 plus 4. And then looking at our bottom numbers, well, I've got 6 and 2, so that is equal to 8. I need to get the other side equal to 8, but I already have that 1. Well, 1 plus what equals 8? That's going to be a 7. What type of atom is that? We go to our periodic table and let's check. Well, 7 is nitrogen, so we're going to fill in that symbol for nitrogen. So we've got nitrogen 15 plus a hydrogen producing that carbon 12 and helium atom, which is an alpha particle. All right, looking at number 3, we've got radon 222 with this star from that crash course video. Anytime we see that star is an indicator of something that is at high energy. And so when we are looking at something like this, that high energy, that's an indicator that this is undergoing gamma decay. And gamma decay, it's not a particle, it's only emitting energy. And so when we look at this, I've got that radon, this is high energy. Notice I already have 222 here. I have 222 here, so in order for those sides to be equal, I can't have any mass. 222 is going to equal 0 plus 222. Well, looking at the bottom, 86 here, 86 here, I also can't have any protons. And so we show that gamma decay or that gamma particle. It is just energy. It doesn't have any mass. So it's that 0, 0 with that gamma particle. And we show high energy at the start, and then it loses its star because that energy was released during that gamma decay. So those are our 3 types. We have beta decay, alpha decay, and gamma decay. Alpha decay, that is the lowest of the energy. Higher energy would be beta decay, where an electron is being released, 0, -1 e. And then the highest energy is gamma decay. If you want, go ahead and give these a try. Otherwise, follow along with me. Looking at our top value, 18 plus what gives me 0? Well, this is going to be an 18. 9 needs to equal what plus minus 1? Well, -1 plus what gives me 9? This is going to be a 10. 10 plus -1 gives me that 9. And I can go to my periodic table and neon is element number 10. This next one, we've got carbon, which is 14, and then I have nitrogen with a mass of 14. So that means I'm going to need a 0 here in order for us to have a total of 14 on both our products and reactants. Looking at the bottom, 6. Well, 7 plus what gives me 6? This is a -1. What has no mass and that a -1 proton? This is an electron, and so this is another example of that beta decay where an electron gets released. Polonium 208. Well, we've got 4 over here, so 4 plus what gives me 208. I've got 204 is going to 204 plus 4 is going to give me that 208. Down here, 84. What plus 2 gives me 84? That's going to be 82. And I can go to my periodic table and find that that is Pb, so lead. All right, here's a periodic table. So now let's write the nuclear reaction. So we have these different types of decay. An alpha particle or alpha emission is that helium particle. Beta decay is an electron, and gamma decay is energy in the form of a gamma ray. So, but no mass and no mass, no protons. And so depending on what it says, we know what particle is going to be breaking off to get an atom that's more stable. So looking at francium 212 decays by alpha emission. Well, let's figure out where francium is. Sometimes with these, the trickiest part is finding where it is on the periodic table because we're dealing with things we haven't really worked with before. Francium is here in that number 87. So I've got francium, it's number 87, francium 212, that's telling us the mass. Decays by alpha emission, so we have that francium at the start, it's going to decay, and alpha emission, well, that means this alpha particle. I know that a helium, 4,2 helium, is going to decay, and then we can figure out, well, what else has to be left in order after that happens. And again, 212 on this side, well, I have 4. 4 plus what gives me 212? I'm going to have a 208 up here. And then same thing, 87 over here. 2 plus what gives me 87? 85. We can go up to our periodic table, and 85 is here, which is astatine. So we're going to have At as the atomic symbol. All right, technetium 99 decays by gamma emission. So with that gamma emission, we are going to have something that is high energy, releasing that energy, releasing that energy to become more stable. Looking at my periodic table, trying to find that element, there's my TC number 43 is what we're looking at. So I've got TC 43. The mass, it told me, is 99. And this is high energy at the start, decaying by gamma emission. Well, I'm going to get that same TC. It's not losing any mass, any protons, but it is losing energy. And so we can show that gamma particle being released. Sodium decays by beta emission. Sodium, looking at our periodic table, sodium is Na with a mass of 24. Sodium is number 11. So decaying by beta emission, well, a beta particle is an electron. And so we're going to show that electron. So 0 with a -1 electron. And this one does get a little trickier because we have that negative. So -1 plus what is going to give me 11? That is going to be a 12 down here. We've got our 24 is going to equal 0 plus what? So we need all 24 up here. And we look at, well, what is element number 12 on our periodic table? We've got magnesium. So we need to, once we know our number of protons, that bottom left number, then we can figure out, or we can put in that atomic symbol. Last one, if you want, try it on your own. Phosphorus 32 decays by beta emission. So again, we've got phosphorus 32. I look at my periodic table. That phosphorus is number 15, decaying by beta emission. If I wanted, I could put my beta particle second. It doesn't matter the order I put them in as long as I have both on this side. So we have 32. So what plus 0 gives me 32? Well, that's 32 here. And what minus 1 gives me 15. 16 is here. So we can go to our periodic table. Element 16 is sulfur. And so we get sulfur 32 and that beta particle as that phosphorus decays. All right, there is a nuclear reactions worksheet. There's a nuclear chemistry check-in, and there is a pivot on types of nuclear radiation that you are going to complete for practice. Reach out to your teacher with any questions.